So, check your email. There's a couple of emails for me. I'm sorry, there's like 3 relating to the exam. Many of you have sent me some questions that I have tried to address in a video that I posted to YouTube, so take a look. The average score on the exam was about 75%. The median or 50th percentile was 79%. I don't assign grades on individual exams. What I do is I wait till the end of the semester, add up all your points, and then I assign grades based on the cutoffs in the syllabus that are described there. That's my starting point, where like 93 and above is an A, 90 to 93, A minus, and so on. Sometimes I adjust those cutoffs downward depending on the median score in the class. In general, in this class, the median tends to be somewhere between a B and a B minus. So if you got a 79%, it's likely not a C plus. It's somewhere between a B and a B minus. Let's see. And then in the lower 50% of the class, the cutoff, for example, between C minus and D is usually quite a bit lower than 70. So even if you thought the exam went rather poorly for you, it may not be as bad as you thought. In order to fail the class, you sort of need to earn less than 50% of the overall points, which is maybe different than some of you were thinking. There are a few people who have not yet taken the exam because of various accommodation issues / emergencies, so I'm not going to talk about specific problems from the exam today. What I am going to do is once those folks have finished their exams, I will make it so you can go back into Learning Suite and see what you missed, see items missed, what your responses were, what the questions were, and then for each item I'm going to try, hopefully get it done fast, a short video describing why the right answer is right and how you would get to the right answer. So hopefully that will disseminate all the information we need as quickly as possible. I understand that some of you will still need to or want to talk to me one-on-one, and I will make time available later this week for that. I will probably send out a link to a Google Sheet, and then you can sign up for a particular time slot, and I'll make sure we'll keep doing that until people stop wanting to talk to me. Which, hey, for my kids is very fast. So let's see. Was there anything else on the exam? Maybe you've seen my email. For a brief time yesterday night, starting about 10 o'clock, it became possible to take the exam for a second time. This was, I did it on purpose, but not so that everybody could do it. There was a student who had internet problems, and by the time they resolved it and got back to their exam, the time had run out and the system had submitted the exam for them, even though they hadn't completed more than about a quarter or a third of it. So huge disaster, and the only way I could figure to get this student back into the exam and be able to take the rest of it, because I guess my Learning Suite skills are suboptimal, the only way I could figure out how to do that was to make the exam available to be taken twice. Now, some intrepid souls noticed that and thought, hey, why don't I give it a shot, and took the exam again. Some of them got a slightly higher score, some of them got slightly lower scores. Of course, the folks with the higher ones want the higher one to count. The folks with the lower scores want the higher first one to count. My intent was not for anybody to take the exam a second time, just to give this one student a chance at finishing what they had started. So I'm going to go with the first score. If you took it again a second time and you think that's terribly unfair and you wish to plead your case, I'm happy to hear your argument. Please send me an email and you can tell me what you feel. Any questions that I haven't really addressed? Okay. All right. Well, today we're going to start in on Chapter 4, which is really kind of fun because we get to now think about organic molecules as not just drawings on paper that are static, but we get to think of their shapes and how they change with time. And honestly, the shape of organic molecules is critical to understanding why proteins adopt their specific three-dimensional shapes. We really aren't going to be able to talk about protein folding in 351. Depending on when and from whom you take 352, you might get a little bit from it. If you get to biochemistry, they'll talk a little bit more about it. But at its core, it has to do with rotation about single bonds in organic molecules. And you're going to develop the basis of that understanding here. Oh, somebody wanted to know how hard was the exam compared to upcoming sections. Let's see, the average was about the same as it has been for this exam given in the testing center without open book, open notes. So what that tells you is this class is more about what you can do than it is about what you can memorize or look up. So that may necessitate a change in strategy for you. You want to view preparation for the next exam like you would think about practicing for a musical performance or an athletic event. You would never try to compress 2-3 weeks worth of practice into the 48 hours before an event. So don't try to do that with OChem. You need to make time for it every day. Also, your practice needs to be focused on areas where you're weak. You're going to identify that by using the study guide and the practice exam long before the exam is open to show you the questions that you get wrong are the things you will struggle with on the exam. So do us all a favor and let's identify those issues ahead of time. Come talk to me, because either way you're going to come talk to me, right? If you get it wrong, you're going to want to come talk to me and we'll talk about why after the fact. But if you do that before, you have a decent shot of actually getting the points, which is what we all want anyway, in addition to the actual knowledge, right? So use your study guides and practice exams to identify specific issues and then focus your study on that. I told the 12 o'clock class that last year I got roped into accompanying the state choir back when it was okay to sing in close company with people, the state choir for state conference. And the state choir master was very ambitious. And she decided that she wanted to do, in addition to Mac Wilberg's Redeemer of Israel, she wanted to do Richard Elliott's arrangement of Let Us All Press On from a few conferences back. It's fun. It's got a really moving sort of, by moving I don't mean emotionally moving, maybe it was for some people, but what I mean is your feet are moving as you play the bass line. In the last version it was hard. I'm not a trained organist. I taught myself to play on my mission when the other elders were playing basketball because no sports skills here. So this was really above my ability, and so in addition to praying and worrying, I would stop into the church on the way to work and I practiced for a half hour or so. And I did it day in and day out, and I focused my practice not on the parts that I could play that sounded good, even though that's the most fun thing to do, but on the stuff that I was just really missing. And by the time performance time came, by the grace of God, we got through it. There were errors all over the place, but none was so bad that I had to stop and say, hold on, wait, that wasn't it. Let's start again, which is all you can really ask for when you're accompanying singers. And so your focus on the hard stuff makes your performance as smooth as possible. So you've got to identify, and I won't know what's the hard stuff for you. You got to identify that for yourself and then work on that. And once you've identified those issues, I can help you. The next exam, what was the average? People are saying, will the next exam be the same as this one? It will be multiple choice. I anticipate that it will be open book, exact same format, similar number of questions. Of course, the material it will cover will be what we're doing now. I think that's everything. Sorry for the digression. Am I missing something, Emma? Okay. All right. So, shapes of organic molecules. For this, we're going to go to our molecules app, and we're looking at a molecule called ethane here. Now, in the noon class, the frame refresh rate was poor enough that this was somewhat difficult for people to see. So I'll try to do it slow enough that you can see it, and what we don't get will draw in a couple of minutes. So this is ethane. 2 carbons, each carbon bonded to 3 other hydrogens, 2 methyl groups bonded together. And we're used to, by now, drawing carbon molecule or organic molecules as sort of stick figures, and we know how to draw carbon-hydrogen bonds that are in the plane of the board versus carbon-hydrogen bonds that are coming out at us. For example, if we drew the molecule from this perspective, we would use a wedge in drawing the bond between this carbon and that hydrogen. In contrast, we would use a dash drawing the bond between this carbon and that hydrogen. And that's good, and that's a very informative way of drawing organic molecules, but we're going to introduce a new one today. And this is one that focuses in on a single carbon-carbon bond. So we're going to focus in on the bond between this carbon 1 and that carbon 2. And we're going to look down this bond from the end so that the two carbons are overlapping each other. Okay? This is called the Newman projection. I have no idea who Professor Newman was. And you may come to hate Newman projections in the same way that Jerry Seinfeld hated Newman on the show. Never could really figure out why, other than Newman was annoying. But there you go. Drawing these conformations could be annoying. By the way, when we talk about shapes of organic molecules, we're going to use the word conformation. This is not an ordinance of salvation. That's not an I there. It is a word that describes the shape of an organic molecule. In particular, different shapes of organic molecules due to different rotations around sigma bonds. So as we look at this molecule from this perspective, it looks like these three hydrogens on the front carbon. It looks like they're separated by 120 degree angles, just because we've sort of flattened our perspective into two dimensions. But in reality, we know that those bond angles are 109.5 tetrahedral, right? Nevertheless, it looks from this perspective like it's about 120. I want to introduce a few terms for describing the relationship between hydrogens on the front carbon and hydrogens on the back. The first term is dihedral angle. Dihedral angle refers to an angle between two vectors. To define a dihedral angle, you need 4 atoms or 4 points. So those points are this hydrogen, this carbon, that carbon, and then let's say this hydrogen. You're really looking for the angle between the vector that goes from this carbon to here and from this carbon to there. If you want to do that mathematically, there's some lovely vector math that can do it. Eyeballing it will be good enough for us. The dihedral angle between this hydrogen in the front and this hydrogen in the back is 60 degrees. Folks at home, could you see those hydrogens I was highlighting? Did they hold green for a while? Yeah, okay, good. Similarly, the hydrogen in front has a dihedral angle of 60 degrees with this hydrogen in the back. Technically, angles change in sign when you go clockwise versus counterclockwise. There is a sign convention that derives from the definition of the dot product, and I do not care what it is because there are robots and programs that can do the math for us. Okay, so I don't care which one is 60 degrees and which one is minus 60. If you know, please, you can tell me, but I will still not care. So there you go. The dihedral angle, let's see, for protons on the front versus the back, when the dihedral angle is 60 degrees, we're going to introduce a term that describes their relative orientation, and the term is gauche. G-A-U-C-H-E. When the dihedral angle theta is 60 degrees, we will say that two groups are gauche to each other. So this hydrogen that I'm highlighting now is gauche to this hydrogen on the back and this other hydrogen on the back. In this shape of the molecule, notice each hydrogen is gauche to two other hydrogens. I don't know why we use that term. I've heard fancy people try to use the word gauche, and I think it comes from the French, to describe something that's boring or passé or maybe, I don't know.
It's to the left.
Oh, to the left. In a political sense? No, it's an idiomatic expression, huh? Okay, all right, whatever. You've got the Democratic hydrogens, you got the Republican hydrogens. Wow, cool. It's interesting, in Spanish, the word left doesn't sound at all like gauche. Where the heck did izquierda come from? We may never know. I did learn from President Worthen a couple years ago that the Spanish word for the letter Y, Y, is literally the Greek letter I. So that's kind of cool. But this is not a class about that kind of stuff. It is a class about organic chemistry. So gauche for things where the dihedral angle is 60. We're going to use the word anti for protons on the front carbon that are where the dihedral angle is 180 degrees with respect to protons on the back carbon. What I mean is, here's this hydrogen, this proton, and it is the dihedral angle between this one in the front and this green one in the back is 180 degrees, and we'll call that situation anti. So gauche is where the dihedral angle between a proton on the front and one on the back is 60. Anti is when it's 180. Some people have asked, why don't we just use cis and trans? And it's mostly, I think, for historical reasons. It would be okay if you said this proton was trans to this one. We use gauche and anti to reflect the fact that these relationships are not permanent in molecules, that they're not permanent about sigma bonds. Sigma bonds involve end-on-end overlap, and that doesn't change when you rotate one group with respect to the other. So we can actually grab onto this proton in the front and tweak it a little bit. Apparently we need to do a little bit more. And we can actually rotate through. Now, this is difficult to see because things are moving quite quickly and we can't label in this program one proton for another. But I want you to watch as I spin the propeller methyl group in the front. I want you to watch what happens and how the dihedral angle changes, okay? And just notice in general. So in this conformation where all of the protons are each gauche to two other protons and anti to another, we call this the staggered conformation. I want, and somebody says, so in reality, they're not actually 60 degrees between them, it just looks like it. Yes, though, actually the way you define the dihedral angle, it is exactly 60 degrees. The thing that isn't exact is if you look at the angle between this carbon-hydrogen bond and this one in the front, it looks like they're 120 apart, but they're actually 109.5. Anyway, I want you to look as we spin around this carbon-carbon bond, and I want you to see what happens as a carbon-hydrogen in the front starts to overlap with a carbon-hydrogen bond in the back, where the dihedral angle approaches 0 instead of 60. All right, so let's see this again. And folks at home will draw this out, so I'm sorry if it's not coming through. One of the things you should notice is if we give it enough of a twist, we're able to distort from having all the dihedral angles be 60 and start to spin. But as the spin slows down, you're going to notice eventually a carbon-hydrogen bond in the front is going to try to decrease the dihedral angle with the one in the back. It's not going to quite get there. It's going to back off, go back down to 60 degrees, and then approach the other one. And it's eventually going to bottom out in this staggered conformation. So see if you can see that again as I spin the propeller. That was ineffective propeller spinning. Now we got to let it calm down. All right. Right round, baby, right round, like a record, baby. Okay, see that? It almost got through and then went back down, okay? The conformation, oh, you can see it on the screen behind if I could angle my camera up. Frame rate is better there. I know it's too slow to see through Zoom, and I'm sorry about that. We'll do this on paper in just a minute. And I just lost everything. Where'd we go? Ethane, there it is. All right. So I'm going to slow this down. The conformation where a carbon-hydrogen bond in the front overlaps with one in the back, or where dihedral angle equals 0. What do you think about that conformation? Do you think it's higher or lower in energy than the one where the double bonds are all, where the carbon-hydrogen bonds are all staggered? Take a look again and see what you think. I suppose that's good enough, sorry. Speed up the simulation and rotate. No, come on. Come on, guy. There we go. Did you see it approach trying to be eclipsed and then backed off? Okay, that conformation where the carbon-hydrogen bonds in the front are all overlapped with the one in the back is called the Eclipsed Conformation because they're covering each other. And that's actually higher in energy than when the dihedral angles all equal 0, or if it's a staggered conformation. So I want you to think about that. We're going to show you how to draw this out now in 2 dimensions, but I felt like having that 3-dimensional picture was important enough to take some time to do it. So here is how you would draw a staggered conformation for ethane from the side. And conceptually, if you want to think about drawing the Newman projection, you'd put your eye in the plane of the page. I'm only somewhat sorry about this. I can never resist drawing the evil Sith eyes. The dark side changes the color of your eyes, apparently, so that's kind of cool. Or contact lenses, whichever you want. If we draw from that perspective, and maybe it'll be helpful, we're going to circle a proton in the front. We'll draw maybe a pink triangle around one, and maybe a blue square around the other, and then I think we'll only need one in the back, so we're running out of shapes, let's make a green star. It's like the worst possible shape I could have drawn in terms of speed. So let's draw it from the perspective that we had in that movie. Looking down the carbon-carbon bond between carbons 1 and 2, here's carbon 1 in the front, and in the back, we can't see carbon 2, so we won't draw it. From our perspective, it would look like the carbon-hydrogen bond between carbon 1 and orange proton is straight up. The carbon-hydrogen bond between carbon 1 and pink triangle proton would be out to our right, and the carbon-hydrogen bond with blue square proton would be off towards our left. Different shade of blue. You've got to be consistent. And then in the back, we would see carbon-hydrogen bonds as follows, and the green star one would be here. Okay? And if you notice, all of the dihedral angles here are equal to 60 degrees. And so this is what we will call a staggered conformation. All dihedral angles equal 60. Now, notice that in this drawing, the carbon-hydrogen bonds in the front should be pointing towards our Sith eyes, whereas the ones in the back should be pointing away. You don't have to use dashes and wedges to indicate this. It wouldn't be incorrect to draw the wedges here to indicate that they're all pointing at you. It's just that most organic chemists know what a Newman projection means, and so it's unnecessary. All right, the relationship between, let's say, orange proton in the front and the unlabeled proton in the back, since that dihedral angle equals 60 degrees, we're going to say these two protons are gauche to each other. However, and that's true for either proton that's on either side in the back for the orange carbon-hydrogen bond in the front. The relationship between orange proton in the front and green star proton in the back, since the dihedral angle equals 180 degrees, we're going to call that an anti-relationship. They are anti to each other. So in the staggered conformations, all dihedral angles either equal 60 degrees or 180 degrees. Right? Now, let's just, any questions you want to ask so far? Somebody asked about torsional strain and why staggered is more stable. Yes, we're going to get there. We're not quite there yet, but we'll get there before the end today. Let's imagine taking your molecular tweezers and grabbing a hold of hydrogen, orange circle hydrogen like we did in that animation, and let's rotate, and let's just imagine that we rotate that orange hydrogen. For the sake of discussion, let's just say clockwise. It could be counterclockwise. It doesn't matter. We're going to choose clockwise just to be consistent through this discussion. And we're going to rotate clockwise by, 60 degrees. When we do that, orange hydrogen should move to this position. Blue hydrogen, blue square hydrogen should move to this position. And pink triangle hydrogen should move here. And now we're only moving the carbon in the front. Like you could really do that, but this is just a thought experiment. And you'll notice that when we've rotated the carbon in the front by 60 degrees, now the carbon-hydrogen bonds in the front all overlap with carbon-hydrogen bonds in the back. It's hard to draw this because if we drew it perfectly, it would look like we were just seeing the carbon-hydrogen bonds in the front and not the ones in the back. So we draw them a little bit offset so that we know they're there. Yeah?
Just for our drawing, does it matter which side that we put, like, for the hydrogens that are in the back? Does it matter if we draw to the left or the right?
Oh, yeah. So for the drawing, if you want to draw this shape where we call this, by the way, the eclipsed conformation. No, it does not matter on which side of either bond you draw this. Some of you may look at this and say, I really wish he had been consistent, and I'm not actually, no, I guess if I had been consistent, maybe I would have done that. It's fine either way. Yeah. We call this the eclipsed conformation because all of the dihedral angles are 0 or 120 degrees, but each carbon-hydrogen bond in front is eclipsed with a carbon-hydrogen in the back. That's the eclipsed conformation. We would say that pink hydrogen is eclipsed with green hydrogen. All right, any questions about that? We've said and noted through that movie that the staggered conformation is actually lower in energy. It occupies the bottom of a potential energy well. It's the most stable conformation available to ethane. The eclipsed conformation is less stable. It is actually higher, it's highest in energy. It is an energy maximum on the potential energy diagram, which we're going to draw soon. And you're going to see that basically the eclipsed conformation is the top of a hill or a transition state in between two different staggered conformations. Notice what happens when we take orange circle proton and again we rotate it through 60 degrees clockwise. what we're going to come up with is another staggered conformation, and it's going to look identical to the first one we were in. The only difference is going to be that our pink and orange and blue labeled protons are going to be in different spots. Now, of course, we can't tell one hydrogen atom from another unless we use isotopic labels, but that's neither here nor there. We can't tell one hydrogen from another, and so the staggered conformation I'm drawing now is going to be equal in energy to the staggered conformation we drew above. We might call the one above staggered conformation 1, this is staggered conformation 2, and it's equal in energy to staggered conformation 1. You can tell that it is. We struggle with this a little bit at noon because we just say, well, they're the same because they're the same. It's hard to find a better way to put it. Notice, like the one above, this staggered conformation, each hydrogen is gauche to two other hydrogens and anti to another, all the way around. So there's no difference between these two. They're the same. So in going from staggered 1 to staggered 2, we go through that high energy eclipsed conformation. And if we were to put this on a potential energy diagram, and if we were to put, say, staggered conformation 1 here, staggered conformation 2 here, we would see that going from one to the other involves traversing a high energy maximum, which is our eclipsed conformation. And we would see that the difference in energy between these two is about 3 kilocalories per mole. All right, so that's great. The question is why? I guess I'll point out, by the way, that if we continue to rotate orange hydrogen, we could get through another eclipse conformation to a third staggered conformation, which would also be equal in energy. We won't do that, but you can, and I think your text takes you through that. Now, the question is why? Why is eclipsed unstable? And why is staggered more stable? There's a couple of ways of thinking about this, and either of them are okay, but one of them gives us, but they give us a chance to think about a new kind of interaction between orbitals in organic molecules that's not so important here, but will become very important later on as we try to explain why organic chemistry happens, why organic reactions happen. So let's draw, I'm going to just copy the, look at one of these eclipsed conformations, copy. And let's focus in on pink hydrogen and green hydrogen. And we're going to draw the eclipse conformation from the side as well. Okay, where here is the pink hydrogen and here is the green star hydrogen. When you're in an eclipsed conformation, notice that the two carbon-hydrogen bonds overlap with each other. They're side to side with each other. And indeed, if we were to draw the sigma bonding orbitals for these carbon-hydrogen bonds, doing so would look something like this, where we're going to use, I don't know, different colors for wave function signs, just to illustrate the differences in wave function sign. And notice that in the eclipsed conformation, the two carbon-hydrogen bonds overlap side to side with each other. Now, we've said before that when orbitals overlap side to side, we call that pi-type overlap, and it can lead to orbital mixing. Sigma overlap is end on end. That's where we get sigma bonds from. Pi-type overlap is side by side. And you can see this as well is if we were trying to draw the same thing in the Newman projection, we would see that these two filled orbitals overlap with each other in the same way that two p orbitals overlap with each other as we're making a pi bond. The problem is that they are both filled. Why should that be a problem? Well, your text points out that in the eclipse conformation, those electrons in the CH bond on the front and in the CH bond in the back are as close as they can get to each other. And since like charges repel, there ought to be some Coulombic repulsion between the electron pairs. Coulombic repulsion, what am I talking about? I'm just talking about the fact that like charges repel. There's another way of thinking about it that's kind of useful and will help you see a reason why the staggered conformation is more stable. We've said before that when two orbitals overlap side to side, we can mix them together to make two new molecular orbitals, one that's lower in energy and one that's higher in energy. And recall that we said the one that's higher in energy is more destabilized than the one that's lower in energy is stabilized relative to the starting position. If both of these starting orbitals, these sigma bonding orbitals, are filled, we're going to fill both the lower energy one and the higher energy one, and we're going to get net destabilization. What we mean by that is this energy difference here is smaller than this energy difference is here. And so when we account for the fact that we have two electrons up higher in energy and two electrons lower in energy, and we're going up higher than we are going low, overall it's net destabilization. This is something that is called closed shell repulsion. And it's the same reason we discussed why helium, a noble gas, doesn't form bonds. Remember that discussion, how we could set up the orbitals just like we did in hydrogen. The only problem is we got 4 electrons instead of 2. And so we fill the higher energy orbital, and that cancels out all the benefits to putting the electrons in the lower energy orbital. So these two, you could think of them as manifestations of the same thing. But I point out this closed shell repulsion to demonstrate the difference between the staggered conformation and the eclipse conformation, because we're going to see that this closed shell repulsion doesn't occur in the staggered conformation. Let's see. Am I missing anything? No? Okay. Questions here? Yeah.
So, are you saying that in the staggered conformation, the anti-sigma bond orbital is less destabilizing, like it's less high on the?
Okay. No, that is a good question, and let me clarify what we're talking about here. We are not talking about sigma star antibonding orbitals yet. We're talking about two sigma bonding orbitals on adjacent carbons, and we're asking what happens when those two bonding orbitals line up with each other side to side. Technically, if they line up with each other side to side, we can mix them together to form a new lower energy orbital and a new higher energy orbital that would maybe correspond to electrons being shared between the two, in sort of a pi type bond and a pi star. It's not exactly that situation, but what we're saying is when the two orbitals line up with each other, we can mix them together to make a new molecular orbital. And we don't even need to worry about what that's going to look like, just that since we have 4 electrons, the whole process is going to be bad and destabilizing. Others? Okay. So let me draw the staggered conformation, and let's look at what that does to this closed shell repulsion situation. Let me just put the carbon-hydrogen bonds in the front like this, and the ones in the back like this. Notice that in the staggered conformation, that is literally as far apart as the sigma bonding orbitals on the front and back carbons can get. There's no further apart than they can go. And so there is less closed shell repulsion here because the sigma CH on the front and the sigma CH in the back don't line up side to side. You see how it's not exactly in line? You remember how we talked about when you take two p orbitals that are in a pi bond and you twist them 190 degrees with respect to the other, that decreases that breaks the bond, it gets rid of the orbital overlap. Orbitals can't mix side to side when they're 90 degrees with respect to each other. But there's something else that can happen here. And to see this, we're going to look at a staggered conformation from the side again, and I'm going to draw a carbon-hydrogen sigma-filled sigma bonding orbital here in the front, or on our carbon that's in the front in the Newman projection. I'm going to remind myself that it's filled. Now I want us to think about the carbon-hydrogen sigma star for this proton in the back. What does a carbon-hydrogen sigma star look like? If this is the bond between the two nuclei, where is the node in the sigma star? Well, one of them is in the middle between the two. It has a lobe here, a smaller one there, and another one here. And every time we go through zero, as we do in between carbon and hydrogen, and then again at carbon, there's a switch in wave function sign. But notice that much, if not a majority, of the sigma star actually points 180 degrees away from the associated carbon-hydrogen bond. It's in the back, okay? So if we were to draw that on top of our molecule here and draw what the sigma star looks like, it would be like this. And this looks kind of similar to what we drew above for the staggered conformation, but the key difference is this orbital is empty, not filled. And if you wanted to draw this kind of overlap between sigma and sigma star in the Newman projection, what you would do is simply draw the large lobe there. There's a node here, smaller lobe there, smaller lobe there. Here's purple, and here's orange. What I've drawn here is what you would see if you looked at this molecule from the side. The one in front is a filled carbon-hydrogen sigma bond, and in the back is your empty sigma star. Okay. Well, who cares? Remember, as we've said, when two orbitals line up with each other side to side, overlap, you can get orbital mixing. Let's examine how that would occur between a sigma and a sigma star. Here is a sigma bonding orbital. And if we know anything about sigmas versus sigma stars, are they the same in energy? No, the antibonding orbital should be clear up here. Okay? Now, when orbitals are far apart in energy, they don't mix together very much. They mix together just a little bit. And what ends up happening is that the lower energy orbital moves down in energy, and it still looks mostly like a regular carbon-hydrogen sigma bond. And the higher energy orbital raises up only just a little bit, and it still looks like mostly a carbon-hydrogen sigma star. But they've mixed with each other, and their energies have changed. So far, we got the exact same situation we had above for the staggered conformation, only we got 2 electrons instead of 4. So those electrons from the sigma bonding orbital get to move lower in energy. The sigma star goes higher in energy. Who cares? It's empty. And overall, our molecule gets stabilized, and the extent of stabilization is about 1 kilocalorie per mole. And we have 3 of these things going on at any given time. So overall, the staggered conformation is 3 kilocalories per mole lower in energy than the eclipsed. This idea of a filled orbital overlapping with an adjacent empty orbital, technically, I mean, it has a name that derives from valence bond theory. It's called hyperconjugation. It looks like pi-type overlap, only it's not involving p orbitals. So we call it hyperconjugation. In pure molecular orbital theory, you actually don't need this at all. But we're going to use hyperconjugation later on as an explanation for why certain things happen in organic chemistry. We're going to call this kind of hyperconjugation the overlap of a filled sigma orbital with an empty sigma star orbital. We'll call it sigma to sigma star hyperconjugation. And that's all you really need to know for now. You need to know that when a filled orbital lines up side to side with an empty orbital on an adjacent atom, they can mix in a way that allows the electrons in the filled orbital to move lower in energy. It spreads them out, it delocalizes them a little bit, they move a little lower in energy, overall more stabilizing. Interestingly, the effect of this process is that the electrons in the sigma bond spread out a little bit in this direction, and the empty orbital itself spreads out a little bit in this direction. Somebody's asked a great question, what does that new bonding hyperconjugated orbital look like? We typically won't draw it because it's confusing. We get the right answers from a pure molecular orbital theory approach. My guess is if you're going to force me to come up with an answer here, I will do so, and you will hate it, but and I won't require you to do it. The filled bonding orbital probably looks something like this. You've got you've got a little bit of delocalization of those electrons into the space between the 2 nuclei. And probably, so that would be your, I'm not sure what we're going to call this orbital. Maybe we'll call him Fred. Lower in energy, and then maybe we'll call the other one that's higher in energy Ethel. I Love Lucy fans out there? Probably not. That show was old when I was little. The sigma star probably looks a lot like a sigma star, only it's going to be spread out a little bit in the direction of the carbon-hydrogen bond on the other side. Maybe even some of it reaching over there, I don't know. Later on, as we deal with some more specific examples of hyperconjugation, I will show you the results from pure molecular orbital theory. And what you're going to see is sometimes the empty orbital that you're dumping electron density into, sometimes that's the LUMO of the molecule. And sometimes that makes the LUMO of the molecule spread out into more than one place. And since this class is all about HOMO attacking LUMO, you want to know where the LUMO is, because if it's in different places, maybe you could get different reaction products. Let me just give you a quick example of that won't make sense. We'll talk about it again in chapter 7. In a carbocation, we've said that the LUMO is the empty p orbital on carbon. But nearby you have these adjacent carbon-hydrogen bonds that are filled that can overlap with the empty 2p orbital on carbon. What that means is this empty orbital spreads out a little bit onto the adjacent hydrogen. And in fact, if you do the MO calculations, what you see is that the bonding orbital for the carbon-hydrogen bond spreads out into the space near where the p orbital is, and then you'll see some of the LUMO is out on that adjacent hydrogen. Why should that matter? Well, if you're a nucleophile, then you got to decide, do I attack at carbon or do I attack at hydrogen? And that can have different consequences. So that's it for today. We'll talk more next time.